And now that we have bond angles and shapes, we're bringing back dipole moment and adding vector addition on top of it. So what we have done so far, this difference in electronegativity, it gives us a basis for the magnitude of a bond dipole. So it's just for that bond. Now, a dipole is a vector, right? It has a direction. We drew arrows showing where the electrons were being pulled, and the difference in the electronegativity gives us a basis for the magnitude. If we do a vector sum of the individual bond dipoles using the VSEPR geometry to figure out exactly which direction and angle those bonds are pointing at, we can show the dipole moment for an entire molecule. So the dipole moment for an entire molecule is going to tell us stuff about the physical properties. So this is an important topic. All right, there will be some vector addition refresher links in Canvas. We're going to look at a couple of examples so that you can see what we mean. So for carbon dioxide, we have drawn the Lewis structure before. It has a steric number of 2, so this linear VSEPR picture doesn't look much different from the Lewis structure that we drew, but you could have drawn the Lewis structure very differently since it doesn't have to show geometry. The difference in electronegativity between carbon and oxygen is 1, so each of these bonds is polar, right? A carbon-oxygen bond is a polar covalent bond. But if you draw the bond dipole for each on top of this picture, I've got on the left my bond dipole. The partial negative end is the oxygen, the partial positive is the carbon. And then on the right side, the partial negative end is the oxygen, the partial positive end is the carbon. I have 2 vectors of the same magnitude because they're both between carbon-oxygen bonds, and in this case, they're both double bonds, that point 180 degrees away from each other. So the sum of these vectors is 0. So carbon dioxide as a molecule does not have an overall dipole moment. So carbon dioxide has bond dipoles. The molecule does not have a dipole moment because those bond dipoles cancel each other out. Let's look at something like water as an example. So the electronegativity difference between oxygen and hydrogen is 1.4. So they're definitely polar bonds. When I draw my VSEPR picture, right, this is a bent structure, my lone pairs coming in and out of the board, right, it's fine if I don't have that indicated here because what I care about are having the angles correct for the bonds and making the vector addition as easy as possible. So one way that you can add vectors is by taking that one vector and thinking about the x component and the y component of that vector, and then you can like take 2 and add them together. If you need to add 3 together, you add 2, get the result, add the third to it, get the result, add a fourth to it if you need to. So each of these vectors, I can take the x components and add them together, and then take the y components and add them together, and then that will give me the x and y components of my resulting vector. So what I have for my bond dipoles, oxygen is more electronegative. So I have a vector that points from hydrogen to oxygen on each side. They kind of point toward each other. If I take the vector on the left, my x component is in the positive x direction, vector on the right, x component in the negative x direction. These vectors are for the exact same electronegativity difference. They cancel each other out. So the x component ends up being 0. But then my y components both point up, My y components add together. So my resulting vector is something that's in the middle of the molecule, in between those two hydrogens, pointing up through the oxygen. So water has an overall dipole, and this is a polar molecule.